Hello, good morning, and thank you so much for joining me here in my shop on October 24th. And I want to thank a number of you for sending me links or information about the schematic or service manual for this radio. Thank you very much. Somehow I missed it. Well, I know how I missed it. There's a number of popular websites to look for schematics. One of them here in Canada for Canadian radio schematics is Pacific TV. And thank you very much, Pacific TV, for doing what you're doing, putting so many schematics freely available on the internet. But as it turns out, a casual search of their website can miss things. And as pointed out to me by one of you, there's a way to dig a little deeper into that website. And presto, I've got the service manual, an excellent service manual for this radio now, which we're going to spend maybe this entire video looking at the service manual as opposed to doing any actual work on the radio. I'm not sure. We'll see how it goes. It's a fairly wordy service manual, but I read it over briefly before the video here, and it's very interesting. A lot of these service manuals, notes on schematics, are coming directly from the engineers who designed these radios. It's them talking to us. So yeah, they write it very formally, but if you think about it, it's not a machine that wrote those things. It's engineers, technicians, design people, and whatnot. So let's take a look at what they had to say about this radio. Okay, here we go. Models A50 and A55. This is an A55 with a Z after it, and the Z apparently indicates this has come from a tabletop version of the radio, and E would indicate it's from the floor model. Same radio though. A 5-tube broadcast and 49 meter band radio. 49 meter band. That's a little more than that. So a little bit of information here. 6A7, 6K7, 6B7. I think that's a little bit of a rarer tube there. The 41, I was talking a bit about this being a rare tube. Well, maybe it's not as rare as I thought. I don't have one, but they are available at commercial suppliers. And not that I think the one in this radio needs to be changed, or I don't have any information about that yet. And a Type 80 rectifier. So that's pretty old. Type 80 rectifier tube. Okay, but we know this radio actually operates, so all these tubes are functional that are in it. Tuning range? Well, that's interesting. So it says 49 meter band. This is the top of the 49 meter band here, and this is just a little bit above the AM broadcast band. And there's not much in here all the way up to about 5,800, 5,900 kilocycles. Yeah, there's a couple stations down around 5, 4.8 I think, which you might be able to receive with this, but that's a little disappointing that it only goes up to 68. Better if it got up into the 9 megahertz range, but interesting. It just picked this low band. This is an evening band. You listen to this one in the evening, not during the day. Alignment, 460 for the IF. Few hints there, I guess, during alignment. Undistorted output, loudspeaker, electrodynamic, which means it has no permanent magnet. So let's read through this, bearing in mind this is the engineer talking to us. Little did he know that he'd be talking to people in the year 2023. The chassis employed in these two receivers are identical. Such distinctions as shortwave reception, wave trap. Wave trap is a I was going to say a type of antenna. Superheterodyne circuit, all metal tubes, diode detection, automatic volume control, resistance coupled audio, tone control, airplane selector dial, and electrodynamic speaker. They characterize the design. Well, these are all kind of standard stuff in a radio. Right here where it talks about resistance coupled audio. So what they're trying to say here is they're not using transformers to couple the audio. in the radio. Earlier radios coupled audio between stages using transformers, and they were problematic. In the early radios, they were very problematic. People kind of got turned off. Plus, they caused tone changes, and they're expensive. Big honking transformers. Tone control. Airplane selector dial. Well, the range of the shortwave band used to be the airplane band, I believe, and the police band was in there too. Airplane selector. Oh, you know what this is? This is describing the nature of the pointer, and that the pointer looks like an airplane propeller. I think that's what they're talking about there. Okay, particular mounting methods are used for supporting the chassis to the cabinet to exclude undesirable microphonic reaction between the speaker and the radiotrons, which is the tubes, and the variable tuning capacitor plates. Now, I've had one radio suffer from this, where in this case the speaker was mounted to the chassis, and you could get the speaker to cause the capacitor plates to vibrate, along with the sound in the speaker. And the result of that is a feedback loop. The capacitor plates vibrate, causes an effect in the output of the radio, which is then fed back to the capacitor plates through vibration. And that's what they're talking about here. Interesting. Also, the tubes themselves can be vibrated. The elements can vibrate and move relative to each other. So the heater cathode can be vibrating one way. The grid is just kind of a loose bag of wires in there. It's going to vibrate. So feedback can occur that way, almost like a mechanical feedback. Antenna ground screw terminals are used to simplify and ensure positive connection of the input leads. So I guess this is an alternative to what? The screw terminals are an alternative to some kind of plug or something? I don't know. I don't know why you get on your soapbox and talk about this. The terminals are also arranged to permit convenient mounting of a double doublet antenna transformer. The double doublet. Never heard of that. An antenna transformer available from the manufacturer. These receivers for use with the highly efficient General Electric all-wave antenna. No idea what they're talking about here, but sell the radio, try to sell the accoutrements with it. Description of electric circuit. You don't call it an electronic circuit. 5 radiotrons are associated in combination with a superheterodyne circuit. 2 of the radiotrons are applied so as to obtain plural functions, thereby gaining, by the way, when I read this earlier, I read it quickly, I got the impression the engineer was trying to use the biggest words he could find, and he's trying to jam as much into each sentence. So this is quite dense writing here. So, well, okay, 2 of the radiotrons are applied so as to obtain plural functions, thereby gaining more than the adequate results normally expected of a 5-tube receiver. So I think what he's saying there is some of these tubes are doing 2 jobs. So even though there's only 5 tubes, it's going to work like a 7-tube radio. So don't be afraid to buy a 5-tube radio, and don't be sucked into buying the 7-tube radio. Ours is just as good as theirs. I think that's kind of what he's trying to say there. In the first stage of the circuit of a type 6A7 pentagrid converter tube, is that proper English? In the first stage of the circuit, okay, there should be a comma there. In the first stage of the circuit, a type 6A7 pentagrid converter tube is employed as detector and local oscillator. So they're using the word detector there. Back in the 30s and 20s, they thought of what we call the mixer tube as a detector tube. Exactly why? I don't know exactly why they do that. So when they say detector, you might be thinking about the detector that comes after the IF. No, they're just talking about the mixer tube here. The tube is employed as a detector and a local oscillator. The related external high-frequency circuits consisting of a tuned antenna transformer with a short wave tap. and a 460 cycle wave trap. There's the wave trap. And when they capitalized it, like it's some big deal. Wave trap and a 3-winding oscillator coil assembly with changeover switches ganged to the antenna transformer shortwave switch. That's a pretty dense sentence for sure. Short wave. So the wave trap is an attempt to stop other radios' IF frequencies from coming into the radio via the antenna, and most importantly to stop this radio from barking out its IF frequency, 460 kilohertz, the local oscillator frequency. Really, it's not the IF, it's the local oscillator frequency. From having that reach the antenna and then work its way into other people's radios in the neighborhood. A lot of radios do not have this wave trap thing going on. Where are we? Within the first detector tube, mixing of the signal and the oscillator voltages is accomplished through electron coupling. Electron coupling. The IF appearing in the plate circuit. So the IF frequency appearing in the plate circuit. If it's there. It's only there when you're, I shouldn't say that. I guess it's always there, but if you're not tuned into a circuit, all that's there is noise. That's at the IF frequency. If the IF system operates at 460 kilocycles as the basic frequency, fantastic. Okay, now he throws the schematic at us, which we will study in a minute. And then we have this oh so valuable diagram showing the wiring in the radio itself, how the wires are to be run, or should be run, where the components are located. Looks neat and tidy in here. You can easily spot where they're using heavier wire, or this is shielded wire or something going on there. Little notes, handwritten notes on it. Wonderful. Oh, here's some more writing. And what are these diagrams here? So this is the speaker. Output transformer, fixed field coil. Must be for the two different radios. Why they didn't label it? They didn't label which is which. The combined second detector audio amplifier AV stage utilizes a type 6B7, a duplex diode pentode radiotron. Wow, wow. Give me a 6B7, hurry man. A duplex diode pentode radiotron. Just sounds like something fantastic in this radio, but this is just a typical detector tube, a couple of diodes and a triode in it. So detector, audio amplifier. Detector's a couple diodes, and the audio amplifier is the triode. Wow, what a mouthful he got there. One diode connects directly to the ground. The other is used for detection. So one diode is ignored in this tube. The other is used. That's what he's saying there. Part of the detected signal is filtered to remove the audible fluctuations and is applied to the first and second stages as a means of providing automatic volume control. So just about every radio does this, because the output from the IF, once it's detected, which really means rectified, you end up with, guess what, a rectified DC voltage sitting there, and that voltage is varying with the audio signal. So what they're trying to do here is they're saying they can filter out that audio variation and use the voltage to control the amplification at the start of the radio. Stronger signal, less amplification, and it throttles the radio's sensitivity in accordance with the strength of the signal being received. Hey, I'm talking like him now. Okay, part of the detected signal is filtered to remove, I reread that. The audio component of the detected signal is amplified by the type 6B7, that's the triode part of it, and conveyed to a resistance capacitance coupling network. I think that's one word, network. A power amplifier Pento Type 41 is used in the output stage and is coupled by a transformer to the low impedance voice coil of the speaker. Full wave rectification is employed in the power supply stage. The speaker field winding serves in the filter circuit as a reactor. Okay, now I don't think I want to read all this until we're getting more close to doing a alignment, because we're just a little hard to. So look at all this. Look at all this stuff here, and look what's coming next. A socket voltage diagram, which is also extremely helpful in trying to identify problems with a radio like this. So great information. This interesting spot here. So somewhere up above, they say, they don't say it down here, but somewhere up in the write-up, they talk about the kind of voltmeter you need. Must be better than 1,000 ohms per volt, which is not a very good voltmeter. A voltmeter affects the voltages it's reading if it's a lousy voltmeter. It's drawing too much power from the circuit under test and will knock the voltage down. But the guys doing this, these diagrams, the engineers doing this, they know this radio is going to be serviced by guys with lousy meters. So rather than give you the laboratory voltages that would be found in a more of a laboratory setting with better test equipment that doesn't draw current, like a vacuum tube voltmeter, an expensive item back then, they, instead of putting those voltages on, they put on voltages that are read with a meter that's typical what service people are using. So usually somewhere in the write-up they talk about what voltmeter they use to make these measurements, to give a hint to people like me and perhaps you what to expect when you use the voltmeter that we're using. Now today, all voltmeters and all those handheld multimeters, they have very high input impedances at 10 megohms or higher, and they qualify as a laboratory quality instrument. Back in the day here, back in the 1930s. In fact, people would fall over if you walked in with a multimeter and said, "Hey, look at this thing I found." Engineers would fall over crying. They would open it up and look inside and go, "My God, this has come from another planet." No, it's just come from the future of Canada, future of the world rather, not just Canada. So I'm really babbling on here. So, and the coffee time indicator's going perfect. Look at this. Cannot be measured with ordinary voltmeter. Now, they didn't really define what ordinary voltmeter means. So I'm sure what it means is a non-vacuum tube voltmeter, an unamplified voltmeter with a low input impedance, 1,000 ohms per volt or something like that. I think somewhere they also recommend using the highest range. Here we are. It is advisable to employ a meter having at least 1,000 ohms per volt, and for each reading to use the highest range that will give an acceptably accurate reading. Highest range because the meter's input impedance is higher on the higher settings. These old meters, not on your new electronic multimeter that we all have these days. So they're also saying, look, general deviations from the values given due to line voltage differences should not be taken as an indication of defective conditions. In other words, if it says, 90 volts and you measure 87, don't go off in a tizzy. Don't worry about it. Really, it's the erratic departure from normal of a single value or group of values that should form the basis of a circuit diagnosis. The erratic. Well, I don't think that's the right word, Mr. Engineer. Hey, you're good at designing radios, but you're not so good with your words. Erratic. And that's the last thing here is a chart of parts. Fantastic manual, lots of writing, engineer really trying to talk to us. Would the guy have any, would he even dare to imagine that someone like you or me would be looking at these diagrams in the 2000s? I mean, that's just unbelievable. Well, here it is. Okay, so I'm going to stop for a little bit, have that coffee because my coffee alarm went off, and then we're going to go through this schematic from front to back, see what we can extract out of it. Okay, here's the schematic, and I think the way we'll go through this, maybe we'll start with the power supply, and then we'll just go through the radio like this, just like the signal goes through the radio. Okay, power supply. So we have a, let's just zoom in a little bit here. Note, transformer tap are on 240 volt, transformer only. Okay, so I think these taps don't exist. So we just have a switch and just goes to the primary. So power is just going to the primary, and that's all. It doesn't go into the radio except on the other side of the transformer. So we have the filaments and the pilot light, or panel light, I think I would tend to call it. And here we have a center tapped high voltage winding going into the type 82 rectified, positive side coming off the heater here, and the heater voltage here would be 5 volts. And so it comes over here, we run into the first capacitor. This could be the one that's disconnected in the radio right now. There's two of them. There should be two fairly substantial capacitors. There's a chance that that box, the square box, metal box, is actually two capacitors. And the two terminals are not a ground and a capacitor, but they're both capacitor terminals. And that's almost certainly what's happened here. So where's the replacement for this and this in the radio? And then there's another smaller capacitor here. Probably its purpose is to drain any RF that is sitting in this area of the radio that has come through from above and has somehow gotten onto this main power line or main supply line here. That's probably what that is. And why not just, why can't this guy drain it out? These electrolytic capacitors don't work well at RF frequencies, so they put in a non-electrolytic capacitor here to just do away with any, ground out any RF that happens to be here. Now, we got to take a look at this. This resistor is the one that's mounted on the side of the chassis, or the apron of the chassis, the back apron. And we have 3 voltages. The ground is at the bottom. In some radios, the ground would be applied here. The chassis would be connected here, and this would become a negative supply relative to the chassis. Not in this one. So there's no negative supply for supplying bias voltage in this radio, but there's something going here, something going here, and something coming off here. 5,000, 3,000, 10,000. This is the 10,000, and this is roughly 10,000, so roughly half the voltage is here. All the voltage is here, though, and all the voltage is here too. Let's follow this line up. This would be the weakest filtered power. And it's going up here. Oh, more filtering taking place. So I have another significant capacitor here, 4 microfarad. That could be the one that's in the back of the radio I was curious about. So there is a little more filtering coming off of here. And now a nice quiet DC available. Okay, and it's heading to what? It's heading to the first tube. So this is a very important filter. This first tube is very sensitive to things. It's intended to be sensitive to the signal coming in on the antenna, but it's sensitive to all kinds of stuff that can be amplified and shoved through the rest of the radio, including hums. It would be a different kind of hum here. It wouldn't quite be an audio hum. It might be an intermodulation hum, maybe. Okay, more power. Now the other side of the filter. So here we have nice clean DC coming out right here. And that's being fed up to the plate. Wait a minute, wasn't I just up here a second ago? So I misinterpreted this. So this feed is coming up, going through this, being filtered here, and I really didn't look that close as to where it's going. It's going into this grid. So So this is acting as a, in this tube they're probably using this grid as a plate. And then they would be using this grid to drive the oscillator. And sure enough, it's connected to these oscillator coils. So you have a little tube inside the big tube. The interesting thing is, you get the oscillator going. The local oscillator is going now 460 kilocycles above the target frequency. So say you're tuning in 1 megahertz, a station at 1 megahertz, right in the middle of the AM dial, roughly in the middle. And so the oscillator here would be running 460 above that, be 1460 kilohertz. The 1460 kilohertz is on the grid here. So it modifies the electron stream going through. Some of that is picked up on this grid, acting as a plate, fed back through this coil, or fed through this coil, gets into these coils, and heads back for the grid, going around, 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 around. This modulated RF, or electron stream in the tube, continues on to the plate, where on the way there it encounters this grid. This is the grid coming back from the antenna, and the signal on this grid is then impressed in the electron stream. The two of them are impressed together. The, what did I say it was, 1460, and the 1 million coming in here, and the two of them are mixed together in the electron stream, and the result is 4 signals coming out on the plate. The two original, the antenna signal and the local oscillator signal, be on the plate here, along with the addition of those two signals, which would be 1 million plus 1 million, 2,460 kilohertz on this line, and the difference, which is 460 kilohertz. It would also be on here. The 460 is going to have a great time in this circuit here. This circuit resonates, is designed to resonate at 460 hertz. The other signals that I talked about, including the antenna signal, will see this kind of like a short to ground somehow. There should be a capacitor on here somewhere. Okay, well, I don't know what I'm talking about, but that's okay. I'll just keep talking anyway. So the other signals are not going to go through this transformer. Just the 460 is going to go through. This side is also tuned to 460. So by the time you get over here, the other 3 guys are gone, and you've got just the one resulting signal. And it's not really 3 signals, because what's on this grid is everything that's on this antenna. Everything is on this grid. Everything is coming through here. Likewise, the converted frequency isn't just the target frequency, it's the entire frequency set coming from the antenna is converted to these other frequencies through the mixing process. So there's a lot of stuff coming out of this tube, a lot of stuff going on in here, a lot. We tend to think of it as, one signal, the station signal and the IF signal, but in fact there's a whack of stuff going on. The whole band is being converted simultaneously. You could put it that way, the whole radio band. Okay, what's all this stuff? This is all designed to make the local oscillator resonate at the appropriate frequency based on the dial setting. And this is the actual tuning capacitor right here. And its brother is, where here, right here, where I'm practically pointing at. So many radio schematics, there'll be a dotted line going through here, over here, and then coming up this way to indicate these 2 capacitors are connected together. Well, they're actually connected together. They're one unit, basically. Well, I shouldn't even say that, should I? But you know what I'm talking about. So, broadcast and short wave. So we are changing the size of the antenna coil here. It did mention in the write-up about a tapped antenna coil, and here it is. So out comes the 460 kilohertz. I can make it through this transformer, And we're on to the next thing. Now, did I finish the power supply? I kind of skipped. I did not really finish it. Let's follow this line. Can't be a lot of voltage on here. Where's it going? So this is driving the screen here. The screen has its own supply all by its lonesome. No capacitors on it. Well, I shouldn't say no capacitors on it because that's what these are over here. Okay, and the plate is getting its feed. Look at the complicated stuff going on in here. So the engineers love this area of the radio. They do all kinds of stuff to affect the tone, including even setting up feedback. I don't know if there's feedback in this radio, but all kinds of stuff. The engineers go wild in this area. They just go wild. Yeah, so we're looking at the screen supply, and then we're down to the ground. And did I follow this one? I didn't follow this one. This one comes up here. Screen. Oops. Grid, screen, and suppressor in there, and it probably goes over here. Look at that. Another 4. Look at it. There's 2 of them side by side. I didn't even see this one. Another very important capacitor. Before the screen goes over here, you see how it's split on this tube? This is the pentode, or many elements inside the tube. It comes up there and there. Yeah, don't ask me to explain it exactly. There's no suppressor grid in here. I can't explain exactly what they're doing. This is another complicated area. How these tubes are handled differently in different radios. It's beyond me to explain it properly, so I won't. Okay, so carrying on, we've made it all the way through this first IF transformer. We then go into the oh so important amplifier in the radio, the IF amplifier. This one has a cathode bias here with a bypass capacitor around it. So that's how it's getting its biasing. Remember I mentioned there's no negative voltage in this radio. So in every case what they're doing is they're pushing the cathode a little bit positive. They push it a little bit positive, then its grid is negative relative to the cathode, which is the key thing. Signal comes out now much stronger, fed through another transformer. By now all the other signals are long gone and there's just the IF signal coming out of here loud and proud for sure. Its output is sent to a little bit of bad drafting there, up to this diode. And the other side, wait a minute, did I get this wrong? No, I'm looking at output. The output here, I don't think that's connected. So I think that's just bad drafting. Comes around, diode, and then this is the cathode here is connected to ground through another big. What are they doing here? So this is another one that's got cathode biasing on it. Look at the size of the bypass. 4 microfarads. Another big capacitor. Okay, well, we don't have any negative voltage, so they decided to do it this way to provide a biasing in here. Did I get that right? Biasing. Yep, on the cathode. Okay, you following this? I'm kind of going around in a bit of a disorganized way, but I keep clicking the button by accident. There I have a trigger finger. Okay, so after being rectified by this diode, the other diode, by the way, is grounded, just as they said, throw it away. I'm not going to use it. Comes down here through a fairly large resistor. Here there's a capacitor to ground. So this side of the coil is grounded. The other side is providing the signal. So now we are coming down here. The capacitor is blocking any DC that's developed in here because of the diode, blocking it from ground. So it's building up. So we have a DC voltage here, 5 or 10 volts. Could be quite a bit more actually. Come down through the resistor, down to this point, where we then enter the shielded cable. It's got a little tiny piece of shielding here, and this is not shielded. Of course, in the radio it may be laid out quite different. It may not look like this inside the radio. So the audio is following this shielded cable to the top of the volume control, but the DC, the DC component also goes to the top. So there's no capacitor blocking it. So there's DC going through the volume control. The DC is blocked here from carrying on this way, and it should find itself. Oh, I would have thought it would go right to ground here, but no, it's connecting to the cathode. I guess. Well, it's a signal ground. So signal ground here. Okay, I have a little trouble explaining this, but that's okay. I don't need to know everything. Can't really know everything. Try as I may, I can't know everything. So now we're going to follow the DC. Now, from here, there's really no current flow in this direction. There's nothing for the current to flow to. It's all open wires or a capacitor like this. So if we picture there's 20 volts here, there would be 20 volts here. There's no current to drop voltage across this large resistor. So let's just go and prove that now. We'll follow this line and find out if there's any way current can flow to ground. Okay, we have a capacitor, no DC can go through it. Going through the coil, coming up here, come down this way, 2 capacitors, no current can flow through it. Here, now a element inside a evacuated glass tube, no current can flow from it. So no current flow, so no voltage drop here, supposedly. But of course, this could be a little leaky. Now this is almost certainly a mica capacitor. It's not leaky. This one could be leaky. That would pull down this voltage a little bit. Not much voltage here, 10 volts or so. But that could happen. Could pull down the voltage. What if it does? Well, then the voltage is less negative than desired. Less negative means less negative bias on this grid. Means more amplification. And the radio would be louder. That's a little surprising, isn't it? Of course, if it's really, it wouldn't have to draw much current to make a voltage drop here. So you'd really lose the automatic volume control effect if a capacitor on this line is leaky, or there's any other path for current to leak off. Got very high impedance here. Tiny amount of charge responsible for the voltage on this line, and a tiny amount of charge change can have a significant a variation on the voltage here because of this big resistor and the super high impedance of this side. Okay, so that's the automatic volume control. Wow, we're finding a lot of these capacitors littered through this radio, but I don't remember seeing them. Okay, now we'll follow the audio. So what's happening here now is we've got the rectified IF output here. The RF has been dumped to ground through this capacitor, and this resistor is making it attractive for the signal to go this way, but DC can't go that way, so it's going to go through the resistor. Now the audio is part of this DC here. I guess that's the best way I can say it. Or the variations in the DC here are generating an audio signal. This capacitor will drop the DC component but carry the AC onward. This is the volume control here. It has a tap on the back. What are they doing here? So I'm going to take a wild guess. This is 1.1 million ohms. Can't be 1 million ohms. Got to be 1.1. Big resistor there. I'm going to guess. Did you hear my guess? This is also similar to this arrangement. This is sending an AVC voltage up through here. So most of these radios, they use the same AVC voltage line, like at the far side of a 2 meg resistor. But here they're using a bit from the volume control. Now I guess the position of the volume control has no effect on what's happening here. It's just a tap on a DC voltage dropping resistor. That's got to be the way this is working. Well, that's what I believe anyway. Okay. Now, the audio signal comes through the capacitor, finds another shielded wire, goes all the way up to the grid. Why shield this wire? Because this is the very sensitive tube or sensitive location in the audio circuits. Any little tiny signal on this line makes a big signal come out of the speaker. That's how it's supposed to work. Just supposed to be the signals you want, not hums or other things. So shielded wire here. And once it's been boosted by this tube, you cannot pick up enough interference to be noticed in the signal anymore. The signal is overwhelmingly strong compared to noise signals, so they don't bother shielding any of this. This capacitor, this is, well, that's interesting, a 0.015, and I found a 0.02 in here, because I changed this capacitor. This is the one I've changed already. Did I make a mistake? 0.02, 0.015, not a lot of difference there. But that's quite a specific size. So the size of this capacitor is going to affect the audio coming out of the speaker. I would say make this bigger, get more bass. So if anything, I boosted the bass here by putting in a slightly larger capacitor. But the important thing was the DC that's sitting back here is no longer leaking charge through here onto this grid, pushing this grid positive. If you remember, the measurement I made was on this grid. There's the grid resistor right there. Okay, so after amplifying this, you see this is like a two-part tube. You could draw a line right down here. And you have the diode part, and then you have the triode part. Yeah, okay. Yeah, don't draw a line. And audio now is reaching the grid of the output tube. And the output tube is going to produce a fairly heavy current in this transformer. That will then induce a similar current out here, and boom, presto, sound coming out of the speaker. This must be a tone switch. This is the tone switch here. Oh, that's kind of weird how that works. It's just sticking a ground onto this line. Okay. Yeah, I don't know exactly how this is doing what it's doing, or what the engineer came up with, but this is the playground for engineers. This area, the detector area, the volume control area, all playgrounds. These coils here and the antenna in particular, all playgrounds for engineers. They all try to do their own thing, I think, and distinguish themselves. Look at my radio. I got good audio, and I only used 2 capacitors and 1 resistor. Look what you did. Yes, Battle of the Engineers. I guess the engineers who were doing this work were among the lead electronic engineers in the world or in the country. This is 1938 or so. There would be a lot of people with this kind of knowledge by now. School set up, all that kind of stuff. So there'd be lots of people with good knowledge. But the designers of these radios would be the top guys, the top dudes. Okay, so we've gone all the way through here. I'm just going to do it kind of blocky rather than so specific. So signal captured here, signal mixed with the local oscillator that's generated down here. Out of it comes a potential component at 460 kilocycles. There's always a 460 kilocycle, but not necessarily a station there, because you haven't tuned the radio to a station, blah blah blah. So out comes the IF signal here, gets through the transformer, gets amplified, amplified, goes through another transformer, detected with these diodes, down through the volume control, back up, out through the triout here that's providing enough voltage swing to operate the output tube, and output tube powering the speaker. This tube, and generally the rectifier tube, the number 80 down here. These two tubes are usually, in these radios, are working hard. They're running hot. They're often physically larger than the other tubes because they run hot. They need to run hot to convey the current. And the result is, to make one of these tubes serviceable for the same length of time as, let's say, this one or this one, this tube would have to be hefted up to the point where nobody would sell it. People would buy the cheaper rectifier tube, and so these guys tend to wear out. I want to say prematurely, but wear out during the life of the radio and need replacement. So one of the reasons why, when I encountered a 41 here, I became doubtful about it being the original tube. Plus the fact that the tube shield is physically too large for the physical size of the tube. But as it turns out, 41. There's another one. What's this? 4. Well, what are they talking about here? 4 microfarads. Where? Here? What is this 4 microfarads doing here? And then this 0.017. Oh, you know what it is? It's tube number 4. and its capacitor. Oh man, well, okay. See, look at that. No wonder I got confused. Okay. That's good. That's it for looking at the schematic. Now, what are the implications of everything that I found here? What's the so what? The so what is learning how the chassis is dealt with, finding out if there's a negative supply here, which there is not, spotting things like the cathode resistors and bypass that's biasing the tubes, spotting things like there's no ground on the speaker out here, it's ungrounded, which may be important for later. What other interesting, or looking at how the power supply is taken care of, and wondering where are these? Where's this guy? Where is he? That's what we'll do. We'll look for these 4 microfarad capacitors. There was one here. Wasn't there 3 of them? Didn't I see 3 in the end? I've lost track of them now. One here. One there. There may be one more somewhere I can't find right now. Let's go see if we can find any of these. Okay, let's go hunting here. Where, oh where are you, small electrolytic capacitors? This could be one. This is possible. This could be one. That's two. That's it. Only two. Huh. This may not be electrolytic. There's another one over here that could be electrolytic. You can't really even see it. It's hidden kind of in here. So what have they done here with this radio then? Because it's pretty clear this is disconnected up here. Maybe if we study the wiring diagram. You know, another way is this capacitor. If this is one capacitor terminal, this is the other, and then the thing is grounded. And you can see they went through quite a length here to solder this on. And did they solder this part? No, this part is spot welded. This piece is spot welded on. So really want to make sure this can was secured. That suggests to me the can is actually one of the electrodes here. So two positive electrodes. They're forming part of a pi filter, and in the middle is the field coil. So if we follow the field coil wires, which might not be so easy to do. Hey, there are the wires I changed down here. These colored ones, down here. Then two of these should go to the two capacitors. Two of these wires should go to the two capacitors. There's nothing down there. Oh, there's something right here. Oh, what am I forgot totally about this one. Okay, let's look at that. That's got two, a little hard for you to see it, got two wires going into it. Yeah. Okay, can we read this? This is the high farad dry electrolytic condenser. You can slide that right off. Black is negative. So it's just one capacitor. 20. This is a 20 microfarads, but there's no 20 microfarad capacitor called for in this radio. But this has got to be an original capacitor here. Am I stupid? Is there another one on here I somehow blanked out on? I don't think so. Oh, so we have the big metal can here. Maybe these are the two. Maybe these are the two fours. The two fours. Hey, that's a special thing in Canada. 2-4. It's held in by this bracket. And it's got two wires coming out, a red and a black. The black is soldered right to the chassis. Black is soldered to the chassis. Look on the diagram. The wiring diagram. That's going to be helpful for that. And then I'll be able to see where these wires are going from up here too, where they were going at one time. And if it's two fours, you know, today a 4 microfarad capacitor, even with 400 volts, a little tiny thing. So even these could be fairly small back in the day. Yeah, let's look at that diagram and see what we can see from it. Okay, down below here is the wiring diagram. So we'll look for that capacitor that I'm curious about, the square one. This would be the square one right here. Capacitor pack is what it says. Let's zoom in on that. It's capacitor pack. Shows a would this be a heavy wire? Why are they showing it like this? Must be a heavy wire going to a resistor sitting here. This is the coil in the can, and this is the open coil. This is up on top. You see how they've dashed all the lines here, all dashed? It's up on top. Can't see it. Range switch. Okay, another. Wait a minute. Yeah, just two terminals on the top. Now one of them comes back this way. attaches here. The other one, a red one, comes back, way back, way back. Oh my gosh, way over to here. To a terminal board. Let's start with that. Let's see if we can spot the terminal board here. And here's a 10. It says 10, but mine says 20. So here's the other capacitor here. I'm just going to look quickly myself at the wiring. So one wire. Oh, this isn't done the same way, because one wire from here goes straight to the chassis. This shows it going to a pin on the rectifier. The other wire goes to a pin on the rectifier. So this is one wire. This one here, which is shown going to this resistor, is gone. This is gone, and they've just tied this to ground. Somebody has reconfigured the power supply in this radio. And remember, it has a low hum. Strong but low hum. Like low pitch hum. Terminal board. Okay, so if it doesn't, so this is going where it's going, just like it shows, and this resistor appears to be missing. The terminal board, is it sitting in there? Wow, I don't see one anywhere. But so here's that board with all the parts on it. I guess I could have reassured myself using this earlier that okay, I'm thinking like three different things at once here. If I'd used this diagram earlier, I could have recognized the run of the wires in this area of the radio better. Figured it out anyway. Look at this wave trap in dotted. Oh, it's up on top. Wave trap up on top. Well, I won't look for that right now. Here's an interesting thing. Look at this. This wire comes out, and then it's just a lump taped. That's kind of odd. They're actually showing the splice here. Okay, it's just things you don't normally find. Well, you wouldn't find them on a schematic, but on this kind of diagram, I guess so. Speaker wires. Okay, well, we're into a weird situation here where somebody has kind of redone this radio a little bit. Now, what's the difference here? If you just soldered this to the chassis instead of sticking a 30,000 ohm resistor there, we have to study this on the schematic. Where's this 10? C35. Right off the rectifier. 30,000, and then the wire goes all the way back to this other capacitor. And then carries on. Oh my gosh, this is okay, let's see if we can spot some of this on the schematic, but this is going to be too much for me to do today. This is a special in itself. So we just kind of go over the top today, and then tomorrow we can look at this much more closely and decide what needs to be done. There is a hum in the radio. Something's got to be done. So, and I just kind of erased what I was going to do. Oh yeah, look on the schematic. So we'll find C35 on the schematic. C35 on the schematic. 26, 31, 32. Hey, how do you get to 35? 35. Here it is, right here. So it's possible what someone has done is they've done away with some of the capacitor filtering in the radio in favor of boosting this part of the filtering. They put a 20 in here, and hope the 4 wouldn't be missed. This 4 wouldn't be missed, or something like that. I'm just making that part up. Well, there's 2 4s right there, a 4 and a 4, right, on the schematic. They're right next to each other. Is that what's been forsaken? Or he stuck another 4 in. I haven't recognized it yet. 10 is there. Where's the 8? Oh my gosh, where is the 8? Okay, so there's some large capacitors in the radio. Let's just examine those and see if we can figure something out there. Oops. Yeah, nothing exciting on the ceiling. This guy here. So there's no. It's really a weird. It's in like a weird condition. It's really just kind of strange looking. We're on our way to replacing this, but I'd like to know a little more about what it is. So it's from the one end of the resistor to the chassis. Maybe I can read back in here. Yeah. Philco. What's a Philco capacitor doing? Now it's got a positive down here and a negative up here. So this is electrolytic. A little further here. Show me a value. Okay, we're going to turn it. This can be damaging to the computer. This really does look like it's redone soldering. 10. There's a 10, but 10 what? There's all kinds of numbers on this thing. Doesn't help that it's all backwards. Turn it all the way. Got to be a 10 at 450. So a 10 at the top of the resistor. Okay, we'll look back at the schematic again here. Top of the resistor, and there's a 10. It's this one. It's this guy here. So we found this one and we found this one. They both look like replacements. This is now a 20 and this is now a 10. So they really boosted up the filtering here. But we haven't found these two. C16 and C34. C16 and C34. C16 and C34. There we are. So that's what those are. So probably they've been replaced with some smaller capacitors, which I just haven't located in the radio yet. But why all the wiring changes? Why didn't he just fit the new capacitors right here? Why? Like, why not just capacitor? He did away with this wire, this component. He's done away with these wires. I'd like to speak to this person. Okay, I think we're going to leave it at that for today. There's enough stuff in my head here. Ooh. So look at this. Resistor board connection. So this is called the resistor board, even though there's capacitors on it. Okay, enough looking. I could do this for another hour. I don't want to. Good. We'll tomorrow we'll look much more closely. We'll nail down what has gone on in this radio. I want to understand what's been done before I start doing stuff, or trouble will ensue. And we don't want trouble. Wait, don't run. This kind of trouble is lots of fun. Fix your radio. Can't make it rhyme. Okay, that's it. I'm done for today. So thanks a lot for watching so far. Didn't do any work on the radio, but that's okay. Need a little bit more certainty before starting to mess around with more parts and the like. Thanks a lot for watching, and we'll see where we get to tomorrow. See ya.